So now that we're finally approaching the end of our limits and continuity unit for Calculus 1, I thought that it would be useful to maybe have a little bit more practice when it comes to determining continuity over an interval and continuity over all real numbers. And so let's actually go ahead and do that. So we have over here e to the 2x, this function, and we know that this is going to be defined. This is going to be defined for all x is a member of R. So we know it's defined for all real numbers. This upside down a just means for all. And one way that we can think about is we can think about the limit definition of continuity over R, if you will. So we know that a function is continuous over R if the limit as x approaches a of that function, and in this case is e to the 2x, equals e to the 2a, or that function evaluated at a for all a is a member of R. And so we know that this is going to be true because e to the 2a is defined for every a value you select. And if we even look at the graph of the function, we can just tell visually that it's actually defined. But even without the graph, we know that regardless of which a value you choose, this limit is always going to be equivalent to e to the 2a. And so by definition, we can say that e to the 2x is going to be continuous over R. And so then let's take a look at this other function over here. And let me pick a nice color because purple. I think this is a nice purple. 2 plus the natural log of x plus 1. We don't really have much of a problem with this 2 over here, but the natural log of x plus 1 does pose a little bit of an issue, because we know that for any logarithmic function, we're only defined whenever the input is strictly greater than 0. And so for this function over here, whenever x plus 1 is greater than 0, strictly greater than 0, then we are defined. Or another way to write this is that whenever x is strictly greater than -1. And so we know that we aren't defined at x equals -1, but we are defined whenever x is greater than, is strictly greater than -1. And if you want to look at the graph of this function, it will look, something like this. And then we will have, our asymptote over here at x equals -1. And you can pick any arbitrary point that gets extremely close to -1. But regardless of how close you get to -1, you're always going to be defined. And there's always a point that's even closer to -1 without being equal to -1. And so we can say that we're going to be continuous as a result, conditionally continuous whenever x is greater than -1. So this is an example of conditional continuity. And then we have these two functions over here. They're two piecewise functions. This is a nice green color. We have x squared plus 1 and 2x plus 7. They're defined for these different intervals over here. And so we know that x squared plus 1 and 2x plus 7 are both going to be continuous over all real numbers. But what we want to do is we want to see whether the piecewise function defined by these two pieces is actually going to be continuous. And so what's important to do is to actually look out for jump discontinuities whenever we're dealing with piecewise functions. And we have to particularly look at these boundary values. So let's think about x equals 0. We know that x squared plus 1 is going to be equal to 1 when x equals 0. And we know that 2x plus 7, so for x equals 0, we know that 2x plus 7 is just going to be equal to 7. And although we aren't actually looking at 2x plus 7 when we're considering f of 0, we know f of 0 is going to be defined by x squared plus 1, but we still want to look, in terms of the limits, in terms of the continuity of this function, we want to look at the point x equals 0. We want to see whether or not these two values are the same. And if you want to actually illustrate what this function might look like, so this would be the quadratic portion, this would be the point x equals 0, this would be the quadratic portion, and then we would have a jump discontinuity, because we go from this point, this is y equals 1, right? We jump all the way up to this point over here, which is y equals 7. And then we continue and we have like our linear function. And so we know that we have a jump discontinuity. And so what we can then say is that we're not continuous. We're not continuous over R. And we can definitely define certain intervals over which this piecewise function is continuous, and I'll leave that up to you if you would like. But in terms of continuity over all real numbers, we certainly are not continuous because we do have a jump discontinuity at the boundary value, which is x equals 0. And then let me just use another color because I enjoy switching colors. We have this piecewise function over here, sine of pi x over 2 and 2 over 3x plus 1/3 for their respective intervals. Another thing we can do, again, let's just take a look at these boundary values, because we know that both of these functions are continuous over their domains, or over all real numbers, I should say. However, when we consider the piecewise function defined by these two functions, then we have to look at the boundary value just to make sure there aren't any jump discontinuities. So for x equals 1, we know that sine of pi x over 2 is just going to be sine of pi over 2, which is going to be equal to 1. So we have that right over there. And then for x equals 1, we also have 2 over 3 times 1 plus 1/3, which is just going to be equal to 2 over 3 plus 1/3, which is in fact equal to 1. And so we know immediately that this function is going to be continuous over R. And why is that? Because if you want to like take a look at what this boundary point might be, so you might have like, this would be the sine function, it would have its maximum right over here, and then we have the linear function, which would continue on, something like that. And we also know that both of these functions are continuous whenever x is, for over all real numbers, these individual functions are continuous. Why is that erasing? These individual functions are continuous, and we were able to determine the fact that at this boundary point, we don't have a jump discontinuity, and so as a result, we can say that we are continuous over R.